Hi everyone, welcome to lecture 24 of your electric circuit class. And lecture 24 is about phasors. So the objectives of this lecture, the first objective is to define and work with phasors. And the second objective is to transform time domain voltages and currents to phasor domain voltages and currents, and of course vice versa. So we will start with phasors. First, let us define a phasor. Is a complex number that represents the amplitude and the phase of a sinusoid. So if you look at over here in this definition, that is a complex number. So let us have some review about complex numbers. The first thing that a complex number is a number of the form z is equal to x plus jy. So now if you look at this over here, we used tilde. We used tilde at the top of the letter just to distinguish it from just a value or a constant value. So in your textbook, if you have a complex number, then that complex number will be in bold letter. So for example, if you have Z, it will be bold Z. If you have a voltage, so in our notes here, we will use a voltage as V tilde, while in your book, it will be a bold letter V. Then that is a phasor quantity. So now, over here we have x plus jy. Of course, that the complex number can take, for example, minus x plus jy. It can take, let's say, minus x minus jy. It can take x minus jy. So all of the possibilities. So now we can define our x here as the real part of Z, phasor Z. Y is the imaginary part of phasor Z, and J is equal to the square root of -1. So any complex number can be expressed in three forms. The first form, we call it rectangular form, and that is phasor z is equal to x plus jy. So when we have rectangular form, the real part and the imaginary part are known. And the second form, that is what we call polar form. And in polar form, phasor z is equal to the magnitude z with a phase angle, let's say phi. So that's why we are saying that you need to distinguish between z, and there is the top of it tilde, and the z over here. So this z is just a magnitude, that is a constant value, just a real number, while this over here is a complex number for this z with the tilde at the top of it. And the third form here is exponential form. And for exponential form, our phasor z is equal to the magnitude z and then exponential of j phi. So these are the three forms. However, we are interested in these two forms, rectangular and polar form. The reason behind that, because in rectangular form we will know the real part and the imaginary part of the complex number, while in polar form we will be able to find the magnitude and the angle or the phase angle. So now to convert between rectangular and polar forms. So if we have the complex number is given as phasor z is x plus jy, so this is here as what we said, that is rectangular. And our phasor z in polar form is z with angle phi, and this is polar form. So now our magnitude z, that is equal to the square root of x squared plus y squared, and this is here called the magnitude of phasor z. Our x is equal to z cosine phi, and our y is equal to z sine phi, and our phi is equal to the inverse tangent of y over x. So that is really based on this triangle here. So this is x, this is y, this is phi, and this is the magnitude z. So from this triangle we will be able to get all of these quantities as long as two quantities are known. So now to convert from polar to rectangular, we use this. Phasor z excuse me, is equal to the magnitude of the phasor, which is z, times cosine phi plus j sine phi, which is equal to z cosine phi plus j sine phi. And if you look at this, that is equal to z cosine phi, it is x, plus j. And if you see this, that is z sine phi is y. So we went from polar to rectangular. And to convert from rectangular to polar, use this, that phasor z is equal to the square root of x squared plus y squared, because this is the magnitude of that complex number, and then with an angle of inverse tangent of y over x. So let us go over an example here. So we would like to convert the complex number z is equal to 1 plus j3 to polar form, and represent it in a phasor diagram. So this is our solution. So the complex number is given in rectangular form. So our phasor z is equal to square root of x squared plus y squared with an angle of inverse tangent of y over x. So we'll just substitute from our expression in rectangular form. X is 1 and y is 3. So 1 squared plus 3 squared, and then the inverse tangent of 3 over 1, which is y over x. And that is equal to 3.16 with angle 71.56 degrees. That is in polar form. And to represent it, this is over here is the real, and this is the imaginary axis. So we have x to be 1, which is this, and this is j3, and this is our phasor z, and this angle here is the 71.56 degrees. So that is the phasor diagram of this complex number. So now let's say that the properties of complex numbers. The first property, that when we have j times j, that is equal to -1. The second property, that j times negative j, that is equal to 1. The third, if we have 1 divided by j, that is equal to negative j. And if we have 1 divided by negative j, that is equal to positive j. And then number 5, if two complex numbers given as A is equal to A with angle phi and phasor B given as B with angle theta, then we can go with A times B, that is equal to the magnitude of A multiplied by the magnitude of B, and then regarding the angles you will just add them together. And if we have phasor A divided by phasor B, that will be the magnitude of A divided by the magnitude of B, then that will be phi. And then since our phasor B over here, it has an angle, whatever that angle, you need to flip the sign when you put it up there. So that will be negative theta. Then we do have 1 over phasor A, that is equal to 1 over the magnitude of that phase or that phasor with an angle of negative phi. And the last thing, that if we have a complex number and we would like to take, let's say, the square root of that, that will be square root of the magnitude, and then our angle will be half of it, that is theta over 2. So half of the angle. So now for number 6, if z is equal to x plus jy, which is phasor z, and that is equal to the magnitude z with an angle phi, then we can say the conjugate or we can say its conjugate, that is better. Then its conjugate, which is z, and then we put a star here, that is conjugate. Then what we need to do, if it is in rectangular form, we will just flip this sign. So that means x minus jy. If it is in polar form, which is this form here, then our z conjugate, that will be z, and you flip the sign of the angle. So now we will know the relationship between time domain and the frequency domain, which is phasor domain. So I can put here time domain representation, and we will have here the phasor. Phasor domain, we can call it also frequency domain. So now, in time domain, if I want to express a voltage, that is V of t is equal to Vm cosine omega t plus theta v. That is the time domain representation of a voltage. To go from time domain to phasor domain, this V of t, we will call it phasor V, and that is equal to, now we take this magnitude over here and we put it there, and then we will take this, we look at this, is that expressed in cosine? Then we can have a direct transformation to phasor domain if that is in cosine. So that is angle, and then we will take the theta v. And if our V of t is given as this, Vm sine omega t plus theta v, then our phasor V, since this one is given in sine, I have to convert it to cosine. To convert it to cosine, we have to subtract 90 degrees. That means our representation will be Vm, which is the magnitude, and then our angle theta v minus 90 degrees. So these are the time domain and phasor domain, let's say, equivalent. So let us go over an example here. We would like to transform the time domain voltage, which is V of t is equal to 12 cosine 377t plus 60 degrees to phasor domain. So this is our solution. Based on our table, we can put phasor V. So this V here, it will become phasor V. And this over here, the Vm. This is cosine, so direct transformation. And we bring this 60 degrees. So this over here is our phasor domain presentation. Let us take another example. Determine the time domain expression for the current I, which is phasor I, is equal 0.2 with angle 36 degrees ampere if the operating frequency is 60 Hertz. So we said that this is the solution. We said that the general format of a current in time domain, that will be Im cosine omega t plus theta I. So in this case, Im is equal to 0.2, which is this value here. And then theta I is 36 degrees, which is this value here, right? And then since we have omega, our omega is equal to pi f and that is equal to pi, and the f is 60, and that is 377 radians per second. So now we can express our I of t. So I of t is equal to Im is 0.2, cosine omega is 377t, and our phase angle is 36 degrees. And this is the time domain expression. So let us take another example here. Transform V of t is equal to 12 sine 377t minus 60 degrees volts to phasor or frequency domain. We have said that for direct transformation, the time domain expression should be in cosine. However, here it is in sine. So first, we need to convert that V of t to be a cosine. To do that, our phasor V is equal to Vm with angle theta V minus 90 degrees, which is equal to 12 with an angle of, our theta V is negative 60, and then we have minus 90. So over here it will be 12 with angle negative 150 degrees volts. And this is our, let's say, the equivalent phasor domain for that time domain quantity. By this, our lecture 24 is done. So as long as you know how to convert from time domain to phasor domain and vice versa, to know what we mean by complex number, and we are using a tilde at the top of each letter if that is a complex number or a phasor, and to know that we do have rectangular form where real plus j imaginary, and we have polar form, and that is magnitude and angle. If you know that, you will be in good shape for this lecture. Over here we have our homework for this lecture, and thank you for watching.